Okay, so I just need a highlighter here. Let me just pick maybe the green one, the green highlight. Okay, so this is discrete mathematics, and we are covering the BITH 212, BCD 212, and BC 212. So I'm going to start with the GCD, or the greatest common divisor. I'm going to start with this algorithm on how can you use this algorithm to find the greatest common divisor of given two numbers. If you're given two numbers, how can you find the greatest common divisor? So the GCD, or the greatest common divisor, written as GCD of AB, is the greatest common divisor of A and B. So given two numbers A and B, they are those numbers that gets into both A and B, and we want the greatest number of those numbers. So that greatest number is the one that we are calling the greatest common divisor. So the greatest common divisor of maybe 30 and 105, which is the GCD of 30 and 105, is 15. So we know that we can put even 5 into 30 and 5 into 105. It can work, but we want the greatest number, or the greatest common divisor that can divide into 30 and 105, and that number is 15. So this algorithm, we've got an algorithm that can help us to find this greatest common divisor. It's the one that you are going to look at. So the greatest common divisor is just the number that gets both into A and B, but that number is the greatest number. Okay, so we're going to look at what we call the Euclidean algorithm, which is an algorithm which is used to find the greatest common divisor of given two numbers. So the Euclidean algorithm is a way to find the greatest common divisor of two positive integers A and B. So the first thing, they must be positive numbers, positive integers. So if you are given two positive integers, how does this algorithm work? So this is the formal description of the Euclidean algorithm. First thing is that you need to input two positive integers, which is A and B. And then after giving the algorithm these two numbers A and B, then the output will be the greatest common divisor, which is what? G. And this greatest common divisor will be the GCD of A and B. That's what it means there. That's what it means. So I need to accept someone to join. Let's make sure that we are on mute. That's the problem with people that joins late. Let's make sure that we're always on mute. Okay. Let's make sure that you're always on mute. If you want to say something, you can raise your hand, or can just interrupt. So let's look at the internal computation, what will be happening when you give it those two numbers A and B. So if A is less than B, that's the first thing. It checks on those two values that you gave it. So if A is less than B, you need to exchange. So remember, I've said that the GCD of what? Of AB. So it's obvious that A must be always greater than B here. So the first number here must always greater than this one. So given that, you need to exchange those numbers. After that, you divide A by B, and you get a remainder R. And if R is equal to 0, or if your remainder is equal to 0, then it means that this B that you have, or the current B, will become your GCD of A and B. Else, so if it is not the case that the remainder is not equal to 0, it means you need to replace A by this B, and then you take your remainder to become your B. And then you do the previous step which is this one of dividing. So you keep on doing that until you find your R as what? As 0. So that's what you do with the Euclidean algorithm. So this is an example using the Euclidean algorithm to find the GCD of 210 and 45. As always, A must be greater than B. That's why we've got our A here and our B here. So we've got our A here and our B here. So we've got 210 and 45, just like that. So the GCD of this, how do you find the GCD of this? So you need to divide this A by B, and then you find the remainder, right? So 45 divides 210 4 times. This one can get into 210 4 times and leaves a remainder of 30, right? That's why we've got 4 times 45 plus 30. If you do this math, you will get 245. You get two. So no, you get a 210. You get a 210. But a lot of people are trying to join. So this simple expression, it means that this 45 gets in 210 4 times, and it leaves a remainder of what? Of 30. So if you say 4 times 45, then plus 30, you're going to get 210. That's the simple mathematics. So because our remainder is not 0, it means we need to replace this A by B and take this remainder to become our B as well. That's why I've got this 45 here. This will become our A here, and then our remainder will become our B here. And then we do the same procedure. We divide 45 by 30, and we know that it is going to be 1, and it gives a remainder of 15. That's why I've got 1 times this 1.30 plus 15 to get a 45 here. So if you look at that, the remainder is 15, which means the remainder is not 0 again. So it means that we need to replace. So it means that we need to replace our A by this B, and then we replace B by the remainder. So this 30 will become our A, and then this remainder 15 will become our B. And then we do the same procedure. We divide 30 by 15, which is 2, and a remainder of 0. So whenever you get the remainder as 0, you report B as your what? As your GCD, right? So therefore the remainder is 0, therefore the GCD of this is 15. So that's how we use this algorithm to find the GCD, of a given number, just like that. So let's look at the application of this Euclidean algorithm. You can also apply the Euclidean algorithm to solve such type of equations. We call them Diophantine equation. So these equations are the equations which are in form of AX plus BY is equal to C. Those equations in this form, we can also solve them using this Euclidean algorithm. So how can you do it? Maybe given this example, find the values of X and Y, given that 182X plus 247Y is equal to the GCD of 182 and 247. So guys, the first things first, you need to find the GCD of this, and then you solve the equation that 182x plus 247y is equal to that number that you get after finding the GCD of this. So first things first, we want to find the GCD of 182 and 247. So these are two positive integers, and then you need to check, is this less than this one? So if it is so, then swap. Why? Because A must be always greater than B. That's why I've got swapped them to get 247 and then the 182 here. And then what's the next? Divides 247 and 182. And then you note the remainder. And then you note the remainder. So if the remainder is equal to 0, report B as the GCD. Otherwise, keep on dividing until you find the remainder 0. So you divide 182 into 247. So it's just 1, and it leaves a remainder of 65. That's why I've got 1 times 182 plus 65. It gives you this 247. If you say 1 times 182 plus 67, it gives you this one. So 247 divided by 182 is just 1, and the remainder of 65. So since the remainder of 65 is not 0, it means that this B here will become your A, and then this remainder will become your B. It's just the rules of the algorithm. So after doing that, then you divide A by B. So 65 into 182 is 2 times, and it leaves a remainder of 52. That's why I've got 2 times 65 plus 52 to get this 182. So 65 divides into or divides 182 2 times and leaves a remainder of 52. Because the remainder is not equal to 0, what do we do there? We make this B to become our A, and we make this remainder to become our B. After that, you divide 52 into 65 is only 1, and it leaves a remainder of what? Of 13. So because, again, the remainder is not equal to 0, we do what we are doing here, replace this A by this B. So this will become our 52, and then replace this B by the remainder. Then you get 13 here. After that, you divide 52 by 13, and then you get 4, and it leaves a remainder of 0. So 13 into 52 is just 4, it leaves a remainder of 0, right? So once you get the remainder of 0, report your B as the GCD. Report your B as the GCD. So this B will become our GCD. So the GCD of this 182 and 247 is 13. Okay. So now we know that we want to solve the equation that 182x plus 247y is equal to 13. That's the equation that we need to solve. Also, guys, take note of this. Writing this, the answers when you are dividing in this notation is very, very important. There's a reason why we are doing that. Why? Because when you are now solving this equation, you need to do the reverse of the algorithm. You start from here, going up until you reach this first statement. By reaching here, you'll be having your answer for x and y. What will be those values? So you need to make sure that you write the solution as you are dividing, going down in this form. Like here we've said 182 into 247 is just 1, remainder 65. So it will be 1 times this value plus 65 to get this 247. So you'll be expressing in terms of what? In terms of I, in terms of A. You'll be expressing your answer in terms of what? In terms of A. Just like that. That's what we'll be doing. So let's look at how we can solve this. So now we want to solve that 182x plus 247 y is equals to GCD, which is what? 13. So this is the equation that we want to solve. So we want to use the reverse algorithm. So how to reverse this? If you go to the last statement, we've got 52, we've got 4 times 13 plus 0. Not this one. If you look at this one, we've got 1 times 52 plus 13 is equal to 65. That's what we have there, right? That's what we have. So if you look at that, from that statement, we have got 13 is equals to 65 minus 1 times 52. Where is this coming from? You are just making the remainder the subject of formula, or you are writing the remainder in terms of this A and this value. Just like that. So you make this remainder subject of formula, and then you use that step. Make the remainder subject of formula, then you use that step till you reach this, or until you use this first part of your algorithm. So if you look here, we are going to have 13 is equal to 65 minus 1 times 52. If you do so, it is going to give you 13. If you really find this one, you are going to get this 13. That's what it means. So we have just said that from here, 13, you're going to make 13 subject of formula. So you can take this one to this side, and then it will become 65 minus 1 times 52. Right? Remember, when we're writing this, we're expressing in terms of A, not in terms of B. Like if you look here, it's 2 times 65 plus 52, which is equals to 182. So if you want to make this subject formula, you can just take this one here. It will become 182 minus this here, just like that. So after having this first step, you have got 13 is equals to 65 minus 1.52. Next thing, you go on the next step, which is the next step, which is this step. And what do you do there? You make this 52 subject of formula, which is 182 minus 2.65, or 2 times 65, right? So you're going to have 65 minus, because remember 52, we know the value of 52. What is the value of 52? The value of 52 is 182 minus 2 times 65. The value of 52 is what? 182 minus 2.65. So we are going to replace this 52 by that value, right? You can even try to simplify that. You can simplify that, but guys, make sure that you do not multiply these coefficients with these values, because those coefficients are the one which are going to give us these values, the x and y. So do not multiply. So if you put this one inside, you're going to get minus 1 times 182 and plus 2 times 65. This is what you are going to get. And then you already have this 65. So this one will be plus 1.65. So it's as good as we are adding 2x, right? 2x plus x. It's as good as you're adding 2x plus x. So if you're adding 2x plus x, you are going to get a 3x. Right? I'm sure you agree here from the laws of algebra. So it's as good as we are saying 2x plus x. So you are going to get what? 3x. That's why I've got 3.65 here. If you look at that, we are not messing around with these coefficients, right? We are still maintaining those coefficients. So we have got minus 1.182 plus 3.65. So after resolving this, now let's go and use the next step. Next step is this one, and we can make this remainder 65 the subject of formula, which means it's 247 minus 1.82. So we are going to replace 65 with the 247 minus 1.182. So you come here, you replace this 65 by 247 minus 1.82. After that, we already have this one, minus 1 times 182. So if you put here, you're going to get, if you multiply here, you're going to get 3.247, then minus 3.182. So if you take minus x, right, minus x, then minus, what is this, minus 3x, you are going to get what? Obvious, you are going to get minus 4x. If you do agree from the rules of what? Of algebra, minus 1 minus 3, you're going to get minus 4. So this is why we have got minus 4.182 here. That's why, because 3 times minus 1, you're going to get minus 3. And minus 3 minus 1 minus 3, you're going to get minus 4. So it will become minus 4.182. I'm taking this 182 as x. So that's why I've got this 3 minus 3x and an x here. So after doing so, now we've got the 13 is equal to 3.247 minus 4.182. If you look at this, it's almost similar to this one. 13 is equal to 182x plus 247y. The coefficient here of y, of 247 is y. So you take the coefficient of 247 to become your what? To become your y. That's why I've got y is equals to 3. And then you take the coefficient of 182, which is x here, 182x. So it also means that this one is the value of x. And because here we've got positive 182, it means that x is what? Is minus 4 here. So x will become minus 4. So that's how you use the Euclidean algorithm to solve such type of equation. So if you see anything like this, it means that you first need to find the GCD. After that, you need to solve this using the reverse algorithm, just like that. So that's all about finding the GCD using the Euclidean algorithm, as well as solving the equation using the using the Euclidean algorithm. I don't know if I've got questions here, but that's all what I have. You can go for more examples, maybe on your slides. Maybe what you are going to do, you are going to look at permutations and combinations. Let's look at permutations and combinations. So a permutation of any distinct elements, which is x1 up to xn, is an order of the n elements x1 up to xn. So for example, here we are saying there are 6 permutations of 3 elements. There are 6 permutations of 3 elements. For example, if there These three elements are denoted by A, B, C, and you are being asked to find permutations of those elements or of that set of elements. What it means is that we are trying to put these elements together in some different order, order. So when you're doing permutation, you need to take in the issue of order, or we are saying that order does matter when you are doing what permutation. It's different from when you are doing combinations. Because combination, we are just looking at combining the elements together. So sometimes if you are doing combinations, CAB is just the same as CBA. That's what we are talking about. So here, if you are looking at combinations, at permutation, you are going to have ABC and then ACB. Maybe you can have BAC, then BCA, CAB, and CBA. So sometimes it's not easier for you to pick that I'm going to have 6 permutation. Why? Because it's not easier for you to just combine all this. Maybe you can make an error there. So sometimes you need to know that the number of permutation of any elements is just n factorial. If you are required to find the total number of permutations that you can form from a given from given set of elements, and just say n factorial, where n is the total number of elements involved in making those permutations. So there are 24 permutations of 4 objects. Since 4 factorial, it will be 24. So n factorial will give you the total number of permutations that you can form from a given alphabet. So in some cases, we need to find the number of permutation of any elements taken at a time. So sometimes you might be asked to find the permutations of n elements taken at a time. When I say taken at a time, you are saying you are taking some of them at a time, not all of them, right? So what do you do on that scenario? So instead of just saying n factorial, what do you do? So if if r is greater than or equal to 1 and less than or equal to n, then the number of permutations of any elements taken r at a time is n times n minus 1, n minus 2, up to n minus r plus 1. So the number of permutations of any elements taken r at a time is sometimes denoted by PNR or NPR. So what could be the formula? The formula is just n factorial, then you divide by n minus r factorial, right? So this one, n factorial, is for finding the total number of permutations that you can form. But if you are saying take an r at a time, you are taking some of elements within the set at a time. Maybe you are saying the set have got 7 elements, but we are going to consider only 5 at a time. It means that we are taking r at a time. So you use this formula, n factorial over n minus r factorial. So for example, how many 2-letter words can be formed from letters in the set A, B, C, D if repeated letters are allowed? So if they are talking about repeated letters, and then you are talking about arranging, then it's a permutation. So if you look at it, we've got alphabet, or the set is A, B, C, D, but you are taking only 2 at a time. Here, how many 2-letter words, right? So you're only taking 2 at a time. So it's a permutation, but taking r at a time. And then our r here is 2 because we're only taking 2 at a time. And the total is what? 1, 2, 3, 4. So our n is equal to 4. And our r is equal to 2. So you can try to list them straight from your head. If you look at that, because we've got A, B, C, D, maybe you can take this A, B first, and then maybe you can take A, C, then A, D. You can take then B, A, B, C, B, C, D, B, D, and then you can take C, A, C, B, C, D, and then maybe you can take D, A, D, B, and D, C. And if you calculate the total number of them, so these are the permutations themselves, right? But maybe mostly you'll be asked to find the total number of permutations that you can form from a given set of elements. So here we are saying the permutation, the total number of permutations, you can just count here, and we must get a 12. but also you can use the formula for PNR, which is n factorial over n minus r factorial. And it is, what is it going to give you? 4 factorial is 4 times 3 times 2 times 1. And then 4 minus 2 factorial, you first subtract, and then you get 2 factorial, and 2 factorial is 2 times 1. And take this one out. You'll be left with the 4 times 3, which is going to be 12, which is this one. 4 times 3, which is going to give you what? Yeah, 12, just like that. So that's how you find the total number of permutations that can be formed taking R at a time. All right. So we can have this question. This is an exercise. How many ways can 5? So someone is trying to join. Someone's trying to join. Okay. So here we've got this question. How many ways can 5 of the letters of the word algorithm be selected and written in a row? If you look at this one, how many ways can 5 of the letters? So you're taking R at a time. Who is this R? Is 5. And then the word algorithm is our alphabet, or is the set of elements that we are talking about. And how many letters are there in the word algorithm? You can count from A here, 1, 2, 3, 4, 5, 6, 7, 8, 9, which means our N is 9 and our R is 5, right? And then now you'll be then now the next thing to do is to just plug those values into your formula, and then you find the number of ways. Right? And then here the question B was say, how many ways can 5 of the letters of the word algorithm be selected and written in a row if the first 2 letters must be TH? So here we have a challenge. Here we've got 5 of the letters of the word, this one. But if you are going to look at it here, there is something which is being said that the first 2 words, we know that they are it's going to be TH. So it will be TH, then we add the other 3 letters to make it 5. TH, we add other 3 letters to make it 5. TH, we something like that. So we need to model that so that we know exactly what is R and what is N, what is our R and what is our N. So let's look at the solution of the first part of this A. If you look at it, the answer equals the number of 5 permutation. So the answer equals the number of 5 permutation of a set of 9 elements, which means we are saying our N is 9 and then our R is 5. So N factorial over N minus R factorial, which means it's 9 factorial over 9 minus 5. And then you are going to find out that 9 minus 5 is going to be 4 factorial. So 9 factorial is 9 times 8 times 7 times 6 times 5 times 4 times 1 times 3 times 2 times 1. And then here 4 factorial, we know that is 4 times 3 times 2 times 1. So that other part of 4 times 3 times 2 times 1 is going to cancel each other out with this part of 4 times 3 times 2 times 1. That's why we only have this as your answer, and you're going to get this number, 15,120 ways. So it's how many ways? So this is number of ways, right? So it's 15,120 ways, right? So if you look at the second one, it says since the first 2 elements letters, or the first 2 letters must be TH, hence we need to choose the remaining 3 letters out of the left 9 letters, which means you are going to subtract 2 from the what? From the word algorithm, and then you'll be left with the 7 alphabets. How is this possible? We are saying that we know that from the word algorithm, TH, we know its position. It's going to be, we know that we are going to have TH at the first. So we are not going to arrange TH. We are going to arrange the remaining. So you are going to subtract from here, so that you know that you are going to subtract from algorithm, you remove TH, and then you are going to arrange only. So your N will become 7. Your N will be reduced. And then your R now will become 3. Why? Because we already from 5 word permutation, it's no longer 5. Why? Because we already know the first 2, so we're only going to look at what, at arranging the only last 3 elements from what, from given 7 what, from given 7 elements. So we are going to have our n as 7 and then 3 as our r. From there you plug into the formula. All right, just like that. Just need to plug into the formula, and plug into the formula is very, very easy. N factorial over n minus r, n factorial. So after that, you know that 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. And then 7 minus 3 is 4 factorial, which is 4 times 4 times 3 times 2 times 1. So that part of 4 times 2 times 3 times 1, you cancel each other with the top part of 4 times 2 times 3 times 1. So you'll be only left with the 7 times 6 times 5 is your answer, which is going to give you 210 ways. So that's how you can do permutations. So mostly that's how you can answer permutations. I don't know if I've got questions on permutations, but if there are no questions, okay, there's a hand by Wellington. You want to say something?
Oh, okay. Thank you, sir. Yeah, I'm really enjoying your lesson. So I wanted to ask, what if maybe you've got repeated letters? You can have some cases whereby maybe you can have more than one letter in that word. How
Okay,
do
wait. Okay, whenever you've got some repeated letters, what you do, you divide by the number of repeating letters. That's what you do.
Oh, okay.
It will be a factor. You divide by the total of the repeating number. If the if the not the repeating number, the repeating element. If the element A is repeating 3 times, you divide by 3 factorial. So if you have got repeating, maybe you've got 3 elements repeating, right? So if the first element is repeating 2 times, it will be, you divide by 2 factorial. If the other one is repeating again by 2 times, it will be 2 factorial times 2 factorial plus super denominator. The other one, if it is 3 times, it will be 3 factorial plus super denominator. You can find some of the examples on YouTube or somewhere there. You can find them. It's very, very easy. Just divide by the total time it is repeating, but if it must be a factorial.
Oh, all right. Thank you, sir.
You're welcome. So let's look at you can lower your hand, so that, yeah, thank you. So that I know that there are no hands which are up. Okay, so ndakubatsira, so I'm sure tinengobva. Okay, so let's look at combinations. Combinations, they are different from permutations. Why? Because on a combination, you are just looking at combining things. The order doesn't matter here. A, B, C, and ACB is just the same thing when you are talking about combinations. So definition, a combination of n elements, x1 up to xn taken r at a time, is the selection of r elements where order does not count. So for example here, there are 4 combinations of 4 elements taken 3 at a time. You are saying you are taking 3 at a time. So if you have got A, B, C, D here, taking only 3 at a time, you are going to have 4 combinations. Right? How are you going to come up with these combinations? You can try to combine A, B, C first. That's what we have here. And maybe you can try A, B, D. That's what we have here. Then you can try A, C, D. That's what we have here. And then you can try B, C, D. That's what we have here. If you try any other thing here, you are going to get a combination which is already here. So just a combination of elements. So you are just combining. The order here doesn't matter. So if you say, I'm going to say B, A, C, it's going to fit here where we have got A, B, C. But it's just a combination. We are just combining the elements. So the formula to find. Let's make sure that you are always on mute. Let's make sure that you are always on mute. Anyway, let's look at if you want to find the total number of combinations of any elements taken R at a time, the formula is just simple. It's any factorial divided by R factorial times n minus R factorial. That's the number of finding total, or finding the total number of the combination that you can form from a given alphabet, So it's as good as we already have, we are using this same formula, but only dividing it by what? By R factorial, this formula here. That's why we've got what? We've got this R factorial. This is the thing that we are just going to add for the issue of combinations, right? So how many committees of 3 can be formed from 7 people? Here we've got 7 people and you want to form a committee, right? From this one, you need to know, is it a combination or a permutation? So I say, how many committees of 3 can be formed from 7 people? Remember here, you are giving you 7 people, and from there you want the possible committees that we can form from that given group. It's obvious we are looking at combining people. It's just a combination. It doesn't matter that maybe, let me just give an example that maybe we've got a committee which have got Susan, maybe James, and Rovimbo, right? So it doesn't matter that if this time I start by picking Rovimbo, and then I'll pick Susan, then I'll pick James, just the same. Even if you try to first pick James and then Susan and then Rovimbo, it's just the same. It's just the same combination, right? So it's just a combination. So each committee is a combination of 7 people taken 3 at a time. So that's the number of committees that can be formed is what? If you look at that, 7 is the n, and then taken 3 at a time, 3 is our r. So it's n factorial over n minus 3 factorial times r factorial. That's the formula here. And you are going to get a what? A 35 as the total number of combinations that you can come up with from this. So that's the formula that you can use. So that's on combinations. You can go and look for more examples on combinations, but that's the formula on combinations. So I think now we can look at the pigeonhole principle. There's what we call pigeon principle. You need to understand it. It's very, very simple and very funny, but some of people will find it very difficult to answer the questions which falls under this topic. But it's very, very simple idea that you just need to follow. So the pigeonhole principle is a mathematical principle that states that if any items are put into k containers, if you've got a total number of k containers and you want to put n items into those with any greater than k, or if the item that you want to put is more than the number of containers that you have, then we know that at least one container must contain more than one item. So in other words, we've got a number of containers there, and then the number of items that you want to put into containers, right? Putting one into each and every what container, right? But if n is greater than this number of containers, it means that there is always one container which is going to get more than one items. So that's the basic of the pigeon hole principle. We are putting the pigeons, or we are putting the items into containers, one at a time, into a container, one into a container, one into a container, one into a container. So if you've got the number of items which are more than the number of what? Of containers, it means that at the end there's going to be one container which is going to have at least one. At least one, it means more than, greater than or equal to 1, right? So that's the pigeonhole principle. So we can take the items as the pigeon, and then we can take the containers as the pigeonhole, or as the holes where we are going to put what? The pigeons. So if you look at this one, we are having these containers 1, 2, 3, 4, 5, 6. So if you look at it, we have got 7 pigeons. So it's obvious that it's evident that if you are going to put these pigeons into holes, there is always going to have one hole which is going to have what? More pigeons. Like this one, you've got at least what? At least one pigeon. This one. So every question that falls under the pigeonhole principle, that's what you need to tell us, that with this scenario that you have given me, there's always one pigeonhole which is going to contain at least one pigeon. That's the basic principle of it. So to show that it is true by the pigeonhole principle, you need to show us that whenever given this scenario, there is, you need to state the pigeons and then the pigeonholes or the holes, and then tell us that if I try to put a pigeon on its own what? On its own hole, it means that there is always going to have what? A hole which is going to hold at least one item or at least one pigeons. Then we are done. That's what we are supposed to do on this topic. So if any pigeons fly into K pigeonholes in the case less than N, some pigeonholes contains at least 2 pigeons. Contains at least what? At least 2 pigeons. So it's supposed to be at least 2, not at least 1. It's supposed to be at least 2, not at least 1. It's supposed to be at least 2 of them. Because the pigeonhole principle, it means that every after putting a pigeon into each and every what, we must get a container again, a truth gender, not 1. Why? Because basically we are just putting 1, but it must be at least 2, not this one. So I think we need to look at that in this slide. It needs to be edited. Maybe I need to edit it now, because I will forget to edit it. I will forget to edit it. Then I will send it to you as it is. Then you have the same issue. All right. So I need the highlight again. All right. So this, for example, here we are saying 10 people have first name Arnold, Ben, Alan. And then the last name and the last names are Razambo, Farani, and more. So these are just 10 people that have got the first name is Arnold, Ben, and Alan. And then the last name is Razambo, Faran, and more. Then the question is saying that show that at least 2 people have the same first and the last names. We need to show that. So I say we've got 10 people here. 1, 2, 3, 4, 5, 6, 7, 10 people. But these 10 people have got a combination of 3 first names and 3 second names. So we need to show that on this group of people, at least 2 of them have got the same name and same last name. How do you do that? Which means we need to know that we have got what? We have got pigeons and pigeonholes. What are the pigeonholes? The pigeonholes are the names, because we want to assign people to this name. We want to assign people to these names. So I need to add someone. Sure, it's already in. Okay, so we need to add these people to names, right? And after that, we can actually see that there is going to be at least 2 people who are going to have the same name. So how this is how possible is this? If you're looking at it, if you are going to match Arnold with these 3 surnames, and then Ben with these 3 surnames, and then Alan with these surnames, because we are saying we've got 10 people, it means that we've got the possibilities that maybe we can have Arnold, and then Ben, and then Alan, right? After that, we are going to have 9 names, right? And then maybe you match, if it is Arnold, you can match with Razambo and then Farani and then more. Those are 3 different people. You can do the same Ben, Razambo, Farani, and more. Those are another 3 different people. You can do again for Alan, Razambo, Farani, and more. Those are 3 again different people. And then we've got 9. From there, if you try to link Arnold and Razambo, it means that you're going to have two people with the same name. Because remember, we've already linked Arnold and Razambo. If you try to say, let me try to link Ben with Razambo, you're going to, again, going to have what? Two people with what? With the same name. So that's what you are supposed to tell us. So there are 9 possible names for the 10 people. So there are only 9 possible different names for 10 people. So if we think of the people as pigeons and the names as pigeonholes, we can consider the assignment of names to people to be that of assigning pigeonholes to the pigeons. So by the pigeonhole principle, some name which are the pigeonholes is assigned to the at least 2 pigeons. So by the pigeonhole principle, you have been actually proved that, or you have been actually showed that at least 2 people will have the same what first name and last name, just like that. So that's how you prove that. And then we've got this example which says among any group of 367 people, there must be at least 2 with the same birthday. Why? Because we know that there are only 366 possible birthdays, right? So if you are going to add another person with a birthday, it's obvious that his or her birthday is going to fall within this 366 possible birthdays. I don't know if it makes sense, but it's just very, very basic concept. It's obvious that we are just going to allocate each and every day of a year a birthday, right? So if you are going to have people, a total number of maybe 378 or 367, it means that the other person to be allocated a birthday is going to give a day which another person was actually born on, which means that here we are going to have what? At least 2 pigeons in one pigeonhole. So we've actually proved that by the pigeonhole principle, we are going to have a pigeonhole which is going to hold at least 2 pigeons. Then if you look here in any set of 27 English words, there must be at least 2 that begin with the same letter. Let's make sure that we are always on mute, unless if you want to say something. Let's make sure that you're always on mute unless if you want to say something. I think the statement was correct to say on the issue of pigeonhole principle, it's supposed to be at least 1 or is at least 2. It's supposed to be at least 1 or at least 2. Is it at least 1? Monica. Yes, you can say something. You can unmute yourself. And so also you can let's spend on kunzwa.
All right. Are you now getting my question?
Yes.
All right. I think the statement was correct to say at least one container will contain 2 pigeonholes, 2 pigeons.
2 pigeons, and it.
One container containing 2 pigeons. So the statement was correct at first. Yeah, that's what I think.
Okay, thank you. That's it. Yeah, that's it. And that's what I've actually corrected. That's what I've corrected. At least 2, not at least 1. Thank you for that. Now we are looking at another example. Okay, this one which was saying in any set of 27 English words, there must be at least 2 that begin with the same letter, since there are 26 letters in the English alphabet. So if you look at this, we have got 27 English words, right? And then if you look at the English alphabet, we've got from A to Z, we've got 26 letters, right? So if you're going to line all those 27 words, it means that it is possible to have at least 2 words that begin with the same letter. Why? Because if you spread these words, maybe you can say each word maybe starting with A, then the other one is B, with the C, with it, whatever. We are going to end at 26. And then when you're going to pick the next word, it's going to start with any of the what? N of the letter, which is from A to what? A to Z, which means you are repeating it. So at the end, there's a possibility that at least two are going to begin with the same letter. Just like that. So here we've got this question which says, what is the minimum number of students in a class to be sure that two of them are born in the same month? What is the minimum number of students in a class to be sure that two of them are born in the same month? This question again requires you to use the pigeonhole principle to solve it. So how do you look at this? If you look at it, we've got only 12 months in a year, right? We only have 12 months in a year. So how many students that we need to be sure that we are going to have at least two students who were born in the same month? So maybe you can have first 12, maybe you can have 12 students, a minimum of 12 students, right? Once you have got a minimum of 12 students, right, it means that maybe you are saying one was born in January, February, what, until we reach December. But if you look at that, we've only assigned this pigeon to pigeonholes, and each every pigeon we've got 1, 1, 1, 1, 1. But by the pigeonhole principle, we are required to have at least two. So by the moment you add another student in the pigeon, it means that by the pigeonhole principle, we have reached the actual, the minimum number, right? The minimum number. So the minimum number should be 13 for you to be sure that you are going to have the students that were born in the same month, just like that. So there are 12 months in a year, and then the pigeonhole principle shows that among any 13, which is the minimum, among any 13 or more students, there must be at least two students who are born in the same month. So that's how you answer such type of questions. And then there's this one which says, let A be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Suppose that, so A is the set, and then suppose that 6 integers are chosen from A. You are going to choose 6 integers from A. And then there must be, or must there be, 2 integers whose sum is 11. So if you are going to pick maybe 6 integers here, maybe you are going to pick maybe 1, 2, 3, 4, 5, 6, right, as integers. We are saying from what you have picked there must be two integers whose sum is 11. If you look at this number that I've actually picked, if you say 5 plus 6, we're going to get 11, which means this one will be true. If you try to pick maybe any other 6 numbers here, maybe different from what I've picked, you are going to find that among those 6 numbers, there are 2 numbers that can add up to what? Add up to 6, or that can add up to 11. So how possible is it? You need to have, or you need to partition this set into subsets, or into subsets of those numbers that can add up to 11, right? And then from there, if you pick 2 numbers or whatever, 2 numbers, if you pick 6 numbers from that, then it is going to give you the sum of 11. Let's look at how to prove that. So first you can take, or maybe you can take 1 and 10, it gives you 11, and then another set 2 and 9, it gives you 11, and then 3 and 8 gives you 11, and then 4 and 7 gives you 11, 5 and 6 gives you 11. If you look at that, we've got 1, 2, 3, 4, 5, right? So each consisting of 2 integers whose sum is 11. So these 5 subsets can be considered as the 5 pigeonholes. If you look at it, we've got 5 pigeonholes. And we are saying we want to assign the pigeons into holes, right? So it's obvious that if you are going to put 6 numbers, it means there is going to be a 1 which is going to have at least two items, right? So if 6 is equals to 5 plus 1 integers are selected from A, then by the pigeonhole principle, at least 2 must be from one of the 5 subsets, but then the sum of these 2 integers is 11. So it's just possible. If you look at that, each and every number here participated here. We have got 1 here, already participated, 2 already participated, 3 already participated, 4 already participated here, 5 also here, 6 also here, 7 also here, 8 also here, 9 also here, 10 also here. So all those numbers participated. So when I'm going to pick 6 numbers here, you know that because you have got 5 sets. So if you are going to pick 6 numbers, the first 5, then when you add another number, that number you find a pair of it that can make it what? That can make it 11. So from here we've got these 5 subsets, and these 5 subsets are the wholes. And then if you are going to pick 6 numbers, it means that you are going to have one whole which is going to have at least what? At least 2 items, just like that. So after that, so that's how you do, or that's how you answer those questions that have got the pigeonhole principle. Go and revise more on it. Go and revise more on it. It's very, very simple and very basic. It's like a kind of reasoning, just a kind of reasoning that you have to do. And then let's look at the proofs. Let's look at the proofs. This is also a part of a part of questions that takes more marks on your exams, which are proofs. Why? Because we've got a lot of examples, or a lot of types of proofs, or a lot of types of what? Of proofing, of methods of proof. So you need to take this topic seriously as well and do all the methods of proof. Do them, right? So we have got the direct proof. We have got the indirect proof. We are going to look at contraposition, contradiction. Also, we are going to look at mathematical induction as well. So you need to be well equipped on this area, Then let's look at direct proofs. So the implication P implies Q can be proved by showing that if P is true, then Q must be also what? True. So this shows that the combination P true and Q false never what? Never occurred. So let's look at some basics that you need when you are doing when you're doing direct proof. So to do direct proof, you need to know these basics, basic 1 to 7. All right. So we are saying it. The first basic is that an integer n is even if and only if n is equals to 2k for some integer k. For a number to be even, right? It's a number which is divisible by 2. Does that make sense? So whenever we are claiming that n is even, it means that there is some certain number that if we divide n by 2, we are going to get that number. So I need to take this call. Okay, sorry. So I was saying that here when you're saying n is equals to 2k for some integer k, it means that maybe let me just have an example of, say, maybe you are saying 4 is even. How can you prove that? If you say 4 divided by 2, you are going to get a 2, right? So you can say 4 is even. Why? Because 4 is equal to 2 times 2. Where this 2 is what? Is our k here. Is our k. So every number which is even, there is a factor here. Whenever you multiply 2 by that factor, you're going to get n. That's why we say that for every number which is an even number, it's just the same as what? As 2k, where k is just the factor. It's the factor here. So any number which will be in form of 2k or 2 times that number, that number is always going to be even. So that's the basic that you need to know about even numbers. What about odd numbers? You need to know that if n is odd, it means that n will be equal to 2k plus 1. Why? Because that whenever you divide any number which is odd, if you divide it by 2, you're always going to get a remainder 1. You're always going to get a remainder 1. So it will be 2k plus 1, 2 times the factor, and then plus 1. If this one was 5, it was going to be 2 times 2 plus 1. If this number was what? Was 5. So it will be 2 times 2 plus 1, where this one is our k. So it will be 2k plus 1. So all the odd numbers will be in form of what? Of 2k plus 1. And then in an integer n, if an integer n is a prime, if and only if n is greater than 1, that's the first thing for a prime number, greater than 1. And for all positive integers, r and s, if n is equals to r times s, then r is equals to 1 or s is equals to 1, right? Remember that from the definition of a prime number, it's a number that can be divisible by 1 and what? And itself, right? So one of this one will be 1 and then the s there. That's how do you know that this one is a what? It's a prime number. So you can go on for a composite number, for a rational number, and for what? For division, if n divides that, if n divides d, here it's n and d are integers and d is not equal to 0, then d divides n. Okay, d divides n, written as d divides n if and only if n is equals to d times k, which means if you say d times k, or d can get into n for some factor here k. So these are some of things that you need to look at, but mostly you are going to look at odd numbers in the even numbers, maybe those that divides for division, and maybe for a perfect square. And a perfect square is the number, like maybe 9 is a perfect square, but 3 squared is what? It's 9. So n is a perfect square. If there is a number that we square it, we can get that number. That's a perfect square, right? So that's what you need for direct proof. You need to know those basics. Then let's look at this one, which says proof that the sum of two odd integers is what? Is even. If you take two odd integers and you add them, you are going to get an even number. So you need to prove that. So if it is silent, it's not asking you to use any other type of proof. So you can just go for direct method of proving. So here, guys, do not try to say, all right, two odd numbers. Maybe I'm just going to take 3 plus 5, and then you say that the number is what? Is even. And then if I try to take this number and this number, so you are being asked that to prove that the sum of two odd integers is even. That's what you are being asked to do. Do not try to say, if I do this, is it going to be even? If I do this, so you need to show, is it even? Is it going to give me an even number, right? And how do you do that? You do it through direct proof, right? So let m and n be two odd integers. Then by definition of odd integers, you can take m to be 2k plus 1, and then you can take n to be 2l plus 1. For some l is an element of Z, and for some k is an element of those real numbers. So guys, if you look at this, we've said two odd integers. So do not take 2k plus 1 for m, and for n you take 2k plus 1 again. It will be a same number. You'll be adding a same number, not two integers. So you need to add two different integers. That's why we've got 2k plus 1 and 2l plus 1. So if we add m plus n, it's as good as you're adding this excuse me, and this. So if you try to simplify that, it will become 2k plus 2l, then plus 1, which is going to give you a 2k plus 2l plus 2. From there, you can factor out 2 both. 2 is common on this one, and then you get 2 times k plus l plus 1. Whenever you have something of this form, you can take this whole thing as your r, and then you have something like 2r, where r is what? Is k plus l plus 1. So what this means, what does this mean is that whenever you get something in terms of 2r, it's just the same as something which is in terms of 2k. And you say that an integer n is even if and only if n is equals to 2k, right? So whenever you have something of this format, it means that that number that we have here is even. And what is that number? It's m plus n. So is what is even. So hence m plus n is even, and we have actually acknowledged that m and n were odd numbers when you take them. So we have actually proved that the sum of two odd integers is what is even. So that's how you do when you're proving by direct proofs. I don't know if I've got questions on this one. Otherwise, I'll be looking at proof by contradiction. I'll be looking at proof by contradiction. So let's quickly look at proof by contradiction. So a proof by contradiction is based on the fact that either a statement is true or it is false, but not both. That's what it will be measuring on. If you're saying that the statement is either true or false, it cannot be both. So proving by contradiction that here's the supposition that the statement to be proved is false leads to logical contradiction, then the supposition must be false. Hence, the given what statement must be true. So what you are saying is proof by contradiction. You are saying if you are saying this thing must be true, right? If you say, no, it is going to be false, it must lead to a contradiction if it is really true. Then that's how you know that this one is what is true. So many theorems in mathematics are conditional statements like P implies Q. So the negation of the implication P implies Q is P and the negation of Q. So that's to prove an implication P implies Q by contradiction method. We suppose that the condition P and the negation of the conclusion Q is true. And ultimately, we arrive at a what? At a contradiction. That's what it is. You are saying you are going to prove what this one is true. And then we negate that. We know that if we negate it, it will flip to false, right? And then we try to prove if it is true. Then it must lead to a what? To a contradiction, which means it is going to give us false because we've negated it. And then that's when we know that the previous given statement was true. That's proving by contradiction. The solution is to contradict with the what? With the basic supposition. So proof by contradiction may be summarized as follows. Suppose the statement to be proved is false, right? That's the first thing. You need to suppose that this statement that you want me to prove is just false, right? And then you show that this supposition leads to logically to a contradiction. And then you conclude that the statement to be proved is actually what? It's actually true. Because as you have said it is true, but then I said it is false, but it actually leads to what? To a contradiction. So it means that the given statement is what? Is true. So let's look at this example which says, give a proof by contradiction for the statement if n squared is an even integer, then n is an even integer. You are supposed to prove that if n squared is even, then n itself is an even integer. That's what you're supposed to prove. But you are using what? Contradiction. So you want to prove that this statement is true, that if n squared is an even integer, then n itself is also an even integer. So we give a supposition. That's the first thing. We suppose that n squared is an even integer. But n is not what? It's not even, which means that n is odd. We are now negating it. You are now what? Negating the result. You have said that if n squared is even, then n is even. But now you are saying, no. Let's suppose that if n squared is even, then n is odd. Then we try to prove it. If it leads to a contradiction, hence the given statement was true. So here we are saying n is odd. So if n is odd, it means n is in the form of 2k plus 1 from these basics that we have been talking about, If a number is odd, it will be in form of 2k plus 1, right? So that's here. So you are saying n squared is even, then n is odd. Then we take our n is 2k plus 1. Let's prove this. Is it n squared going to be what? Going to be odd, right? Boom. So you put n squared here. So you square this n. So you square both sides. And then you get, if you expand this one, you're going to get 2k times 2k, 4k squared. And then 2k times 1, you're going to get 2k. Then again, you are going to 1 times 2k. Then you're going to get a 2k. If you add that, you're going to get a 4k. And then 1 times 1 is going to give you a 1. That's what you do when you're expanding. After that, if you look at these two things, you have got a common factor, which is 2. If you factor out the 2, you're going to get 2 times 2k squared plus 2k and then plus 1. If you look at that, you are going to get 2r plus 1 as what? As a form of what? Of an odd number, right? As a form of what? Of an odd number. So n squared have shown us to be what? To be an odd number. That's contradicting. If you are not seeing the contradiction is that we are saying that if n squared is an even integer, right? Then n is what? Is odd. This. But when you put n as an odd number, n number would are odd, and would are even. So there is a contradiction of this statement, which means the given statement before was true that if n squared is even, then n is what? N is even. Why? Because when you've tried to negate this one, it gave us the wrong answer. It gave us the what? This one, instead of being even, it gave us the odd number. N squared is an odd number. So this shows that n squared is odd, which is a contradiction to our supposition that n squared is what? Is even. Hence, the given statement is true. Excuse me. So that's how you prove using contradiction. I don't know if I've got questions on proving by contradiction. Contribution. So if there are no questions, contribution, I can move on to proof by contrapositive or contraposition. Just the same way, almost the same way with what we have done, but only that you need to find the contrapositive of a statement, and then you prove the contrapositive of the statement. So if proof by contraposition is based on the logical equivalence between a statement and its contrapositive, you are saying the given statement and its contraposition and its contrapositive, they're just the same or they're equivalent. So if you prove the contrapositive of the statement and if it becomes true, it means the given statement is also true, just like that. So the contrapositive is usually proved directly. Only what you need to do is to find the equivalent contrapositive of a statement, and then you do direct proof. So the method, so the first thing is you need to express the statement in the form of if P, then Q. After that, rewrite this statement in the contrapositive form of not Q, then not P. So if you look at this, all right, so if you look at this, the P implies Q. Its contrapositive statements, the negation of Q implies the negation of P, right? So first thing you need to write in terms of P implies Q, and then you write it in terms of contrapositive, which is the negation of Q implies the negation of P. This is if not Q, then not P. And then prove the contrapositive by direct proof. So like this one, which says prove that for all integers n, if n squared is even, then n is even. Just the same like this. That we've proved, but here I've proved is a contradiction. So let's see when I use contraposition, what are you going to do? So the contrapositive of the given statement is that if n is not odd, if n is not even, then n squared is not even. That's the contrapositive of it. Remember, we are saying if n is squared, then n is even. If n squared is even, then n is even. So if P, then Q. The negation is, if the negation of Q, then the negation of P. So here we are saying odd, odd, but we are going to start this one implies this one, just like that. So if n is odd, then n squared is odd. Simple. That's what you are going to try to prove. So we prove this contrapositive statement directly. Suppose, so we are saying suppose n is odd, which means our n is 2k plus 1. For some k, it's an element of set. So n squared will become 2k plus 1 squared, and then you multiply it, and then you simplify, you get your n squared as odd number. Hence, n squared is odd. So thus the contrapositive statement is true, and so the given statement is what is true. Why? Because we've said if n is odd, then n squared is what is odd, right? If n is odd, then n squared is what? If n is odd, then n squared is odd. And we've put our n as odd here, and then we've get n squared here. N squared is what? Is an odd number, which is true. So we can clearly see that by contrapositive, the given statement was true. So that's how you do, or that's how you answer the question using contraposition, using proof by contraposition. So you can do the same here. You can try to prove this one by contradiction and contraposition as well as an exercise. N cubed plus 5 is odd, then n is even. Try it using contrapositive, try it using contraposition as well. I think it's a good question for you to exercise. But such of this exercise are the ones that made up your exams. So let's look at the principle of mathematical induction, but I'm sure that there are no questions on contradiction and contrapositive. So that I'll look at principle of mathematical induction. I'm sure we are good with that. So let's look at the principle of mathematical induction. So guys, on principle of mathematical induction, there are rules, there are steps that you need to follow. Do not jump any step. Otherwise, it won't be the principle of mathematical induction. Proof by mathematical induction have got 3 parts of it, and you have to follow them. Failure to do so, I don't know what you'll be doing. Why? Because it's no longer the principle of mathematical induction. Remember, these are rules which are there for you to prove that this is true. So you need to follow them step by step. You need to know them. You've got the basis step, you've got the hypothesis step, and then you've got the inductive step. You need to have them when you're doing principle of mathematical induction. Failure to do so, it's no longer mathematical induction. So given Pn, which is a propositional function, a proof by mathematical induction has 3 parts. A basis step, where we show that P of 1 is true. And then the inductive hypothesis step. I need to add someone. And then the inductive hypothesis step, where we assume it is true for P of k, and then an inductive step where we show that for all positive integers k, if P of k is true, then also P of k plus 1 must be true. Once you have done that, you know that you have done the principle of mathematical induction. And the given statement was true if you find it out to be what? To be true. So to prove that P of n is true for all positive integers n, where P of n is a propositional function, we complete 3 steps. The basis step, we verify that P of 1 is true. When I say P of 1, you can put any number which is within the required set, right? You can say from n is greater than or equal to 2, it means 1 will be out. You'll be starting from 2, and you can take any number, you can substitute, and you see if it is true. And then the inductive hypothesis step, where we assume that P of k is true. It's just the assumption that you make it the inductive hypothesis step. And then on the inductive step, you use the hypothesis step and the inductive step to solve. So if you fail to use the hypothesis step when you are doing the inductive step, it's no longer principle of mathematical induction. So somehow you need to use this step here. So we need to show that the conditional statement P implies P of k implies P of k plus 1 is true for all positive integers k. That's what you need to show. So you are going to use this P of k to show that if it is true for P of k, it must be also true for what? For P of k plus 1. So to complete the inductive step of a proof using the principle of mathematical induction, we assume that P of k is true for any arbitrary positive integer k, and show that under this assumption, P of k plus 1 must also be true. So the assumption that Pk is true is called the inductive hypothesis. So that was just an hypothesis, but use the hypothesis at the inductive step. So if we got this example which says 1 plus 2 squared plus plus 2 to the power n, we always equals to 2 to the power n plus 1 minus 1 for all non-negative integers. So that's what it's saying. It's like given this formula, you can generate all these numbers. That's what it says. So it's saying for all non-negative integers, right? For all non-negative integers. So you can put 0, you can put 1. A 0 is a positive integer. So you can put a 0, 1, 2, 3 going up, right? In that, and you still get that's the claim. So you need to prove using mathematical induction that this formula can really generate that series. That's what it means. You need to show that. So how do you show that? How do you show that? So solution, let P of n be the proposition function that 1 plus 2 squared plus to plus 2 to the power n is equal to 2 to the power n plus 1 minus 1. Right? That's what we have. And then on the basis step, you can put any number and try to prove that the left-hand side will be equal to the right-hand side, right? So you can put here onto the power n, you can put P of 0, and then you check if it is going to true, and then here you put also 0 at n. So on the left-hand side, you're going to get to the power 0 is going to give you a 1, and then to the power 0 plus 1 is going to be to the power 1 minus 1, which is also going to give you what? A 1. So since the left-hand side and the right-hand side are equal, it means on the basis step, P of n is true, right? And then you need to go on to the what? On the you need to go on the hypothesis, step before doing the inductive step. So for the hypothesis, for the inductive hypothesis, we assume that P of k is true for any arbitrary non-negative k. That is, we assume that 1 plus 2 squared plus 2 to the power k. Here on n, you are putting k is equals to the power k plus 1 minus 1. So yeah, we just assume that this is true. That's the assumption that we make. And then after that, we need to do the inductive hypothesis, where we are going to use this part on the inductive hypothesis, we're going to put k plus 1 for n. After that, we need to prove that if it is true for k, it must be true for k plus 1. That's what we are supposed to do, right? For these numbers, just the numbers of 2 to the power something from 0 up to n. Here, 2 to the power 0 is 1, then 2 to the power 1, that's 2 squared, 2 to the power 3, 2 to the power 4, up to 2 to the power n. That's what's happening here. Okay, so what do you do here? It's 1 plus 2 plus, so you are just taking this one. We've already putting a k, which is this one is equals to this one. We'll take a k up. So when you are putting k plus 1 is the next term after when you put k. If you are looking at it here, we are putting a 0, you're putting a 1, you're putting a 2. So the next one, you put a 3, the next one you put a 4 up to what? Up to n. So if you put a 2k here, right, a 2, if you put k here, so the next thing we will have to the power k plus 1, the next thing we have 2k plus to the power k plus 2, something like that, right? So here, for when you are going to put 2k plus 1, it's obvious it's going to be 1 plus 2 to the power 2 plus to the power k, and then plus 2 to the power k plus 1. It will be equal to, then for n you put k plus 1. So here to be to the power k plus 1 plus 1. That's why we've got to the power k plus 1 plus 1. Then minus 1, which is going to be to the power k plus 2 minus 1, something like this. Will be equal to this whole thing, right? So how do you use the hypothesis step from this one? If you look at it, so at this moment, you need to say, consider the left-hand side. After considering the left-hand side, you need to prove that it is equal to this one. Take note of this, guys. You need to take the left-hand side and then you prove that it is equal to the right-hand side. So you need to take this whole thing, write it in this form. If you reach this form, you can safely say that by mathematical induction, it is true, or the given, this one, the given statement is actually what is actually true. So how to do that? If we look at this part right here, if you look at this part right here, this part, I'm sure you are seeing it, this part right here. If you look at this part right here, you will see that this part is just the same as this part, right? Which is our hypothesis. It's just the same with this part, which is our hypothesis, right? So you can even take this and substitute it here, and then you can work this one. So that's how you can use the hypothesis part on this one. So if you look at that, you are considering the left-hand side, this one is equals to, if you look at it, we have taken this one that we have put into bracket, which is the hypothesis part, plus 2 to the power k plus 1. And then if you are looking at it, we are going to replace this part with the hypothesis step, which is with 2 to the power k plus 1 minus 1. That's what you are going to get here. After that, you solve the left-hand side. But when you are solving it, you need to be in, you need to know that in mind, I need to produce something like this. So you need to work towards that, whichever possible way which can give you that. That's how you need to model that. So if you look at it, we've got 2 to the power k plus 1 minus 1 plus 2 to the power 2 to the power k. After that, we've been arrived at 2 to the power, at 2 times 2 to the power k plus 1. Where are we getting this number? Where are we getting this number? If you look at that, 2 to the power k plus 1 and this number, let's just take 2 to the power k plus 1 is what? Is maybe x, is maybe x. If you say x plus x, you are going to get 2x, right? So it's just the same as we are saying x plus x. You're going to get 2x. That's why I've got 2 dot 2 to the power k plus 1 and then a minus 1. Because this bracket, you can just move them because we are just adding. There's nothing here. We are not multiplying. So after getting this, you need to take note of this. These bases, they are the same. We are just using laws of indices, I am sure, from your O level. If you are saying x times x, sorry, I'm using a mouse. I'm not using a pen. My laptop is not a touch screen, so I'm not just using a pen. So yeah, be patient with me. Some more things that I write here. So if you are saying x of x times x, you are multiply this thing, you've got the same base, right? So you can actually add the powers, right? To give you what? 1 plus 1 to give you 2, so it will become x squared. X times x is x squared. That's what it is, right? So if you look at this, this one is 2 to the power 1 times 2 to the power k plus 1. So these bases are equal, so you can add powers. So what are these powers? We've got k plus 1 and then plus 1, which will give you k plus 2. So it will become 2 to the power k plus 2 minus 1. And if you look at this thing, it's familiar. We've seen it here, right? So we've managed to prove that this left side is equal to the right-hand side. So by doing so, we've managed to prove using mathematical induction, or the principle of mathematical induction. So note that we use the inductive hypothesis in the second equation in this string of equalities to replace this part by this part. So we have completed the inductive step because we have completed the basis step and the inductive step. So by mathematical induction, we know that P of n is true for all non-negative integers. So that is 1 plus 2 plus plus 2 to the power n is equals to the power n plus 1 minus 1. This 2 is supposed to not be at the power. So 2 to the power n plus 1 minus 1 for all non-negative integers of n. You have proved that. That's how you prove using the principle of mathematical induction. So let's look at proving the divisibility. When you want to prove using mathematical induction, but those ones which you'll be asking for division to show that it is divisible by a certain number, so that it is divisible by a certain number. So mathematical induction can be used to prove divisibility results about integers, or for example, use mathematical induction to prove that n cubed minus n is divisible by 3 whenever n is a positive integer. Take note of this, guys. This statement is very, very important. It's saying use mathematical induction to prove that n cubed minus n is divisible by 3 whenever n is a positive integer. So on the basis step, or on the first step, do not take negative integers and try to plug here. Otherwise, you end your workings there, saying that no, it's not divisible by 3. Why? Because I've put this number and it didn't give me a number which is divisible by 3. Because at first you just put it, you just do a direct proof, you just put a specific number from this set, right? So you need to take note of this n, that it is valid only for those positive integers. All right, so solution: to construct the proof, P of n denote the proposition that n cubed minus n is divisible by 3. So the basic step is that the statement of P of 1 is true. Because why? Because if you put 1 to the power 3 minus 1 is going to give you a 0, and 0 is always divisible by 3. 0 divided by 3, the answer is what? It's 0. So this completes the basic step. You can try any number. You can put a 1 there. You can put a 2 there. You can put a 3 there. What you get, it's a number which is divisible by 3, right? But that alone is not enough, because you cannot test up to positive infinity. So we need a way that can tell us that if it is true for this only specific numbers, or it must be true up to what? Up to positive infinity. So you need to go for the hypothesis, where you say it is true for P of what? For P of k. So for the inductive step, suppose that the statement is true for n is equals to k, which means if it is true for n is equals to k, it will become k cubed minus k here, n cubed minus n. So it will become k cubed minus k is divisible by 3. So if a number is divisible by 3, remember it will be in form of 3 times q. Why? Because q will be the factor, the number of times that 3 can get into here. So it will be in form of 3 times q. So you mark this equation. You need to use this equation when you're doing divisibility. That's how you do it. You need to use this equation on the inductive step. So on the inductive step, we say we need to prove that for k plus 1, it must be, if it is true for k, it must be true for k plus 1. So we need to prove that k plus 1 cubed minus k plus 1 must be divisible by 3. That's what you need to prove. So it must be also true for k plus 1 to the power 3 minus k plus 1 must be divisible by 3. So how do you show that? We need to show that this number is divisible by 3. So k plus 1 to the power 3, you multiply this one, or you expand this. So it will give you k cubed plus 3k squared plus 3k plus 1. Then minus this k plus 1. After that, you need to reduce it into its simplest terms. This plus 1 and minus 1, you cancel each other out, yes. And then we've got this 3k minus k will give you a 2k here. And then this 3k squared will remain 3k squared, and then k cubed will remain k cubed. I've talked too much. Let me try to finish this. Okay, trees. Then after this, what do we have? K cubed minus k. We've got k cubed. Okay, there's this simple magic, guys. Remember, that we want to prove that it is divisible by 3. So you'll be trying your best to work towards that solution, to have something that is divisible by 3. And we know that anything which is divisible by 3 is something which is in terms of 3R or in terms of 3L or something like that. It will be something that will be in divisible by 3. So you want to move towards that. So if you look at that, they are saying that maybe we can just adding we can just adding a k and subtracting a k at the same time. Why? Because you want to use this step which says k cubed minus k. So they are trying to say, because we have already this k cubed, right? This k cubed. So we can maybe add a k cubed minus k here. At the same time, we add k to that expression. So it's as good as if you are saying minus 1, then plus 1. You always get a 0, right? So it's as good we have add nothing here. We have add nothing here. We have subtracted a 1 and add a 1 at the same time. So we are subtracting a k here. K cubed minus k, something totally new which wasn't there. At the same time, we are adding a k here. So it's as good we are saying k cubed minus k, and then we're adding a k again, which means we are saying minus 1 plus 1 is a 0. So you're adding nothing, we are subtracting nothing. So by doing so, we have k cubed minus k plus 3k squared plus 2k plus k. This 3k squared is already here. This 2k is already here. So you only introduced this thing and this thing, right? That's what it is. And then after that, it's like we already know that this, and if you add this one, 2k plus k, you are going to get a 3k squared. And we know that this thing, we have seen it somewhere in our hypothesis. We have seen it here on this equation. So using equation 1, we know that k cubed minus k is equals 3q. So we can take this 3q and substitute for this one. So that's how you use the hypothesis, the inductive hypothesis for divisibility. So we are going to have 3q plus 3 times k squared plus k. Where is this coming from? We are just factoring out 3 here. So we can even go back here. You can multiply here by 3k squared, and then you get 3k. So you can go back here. So after doing this, you can now factor out a 3, because 3 is now common on these two things. Then you end up having 3q plus k squared plus k. After having something 3 times all this thing, it means that this number is divisible by 3. Why? Because you can take this one as maybe r, right? So it will become 3 dot r. So it means 3 dot r is always divisible by 3. Why? Because if you divide by 3, you're going to get r as your answer. So r maybe is just a positive integer. It's just an integer there. So it means that this number is always divisible by 3. So once you arrive here, you can actually say that hence by mathematical induction, n cubed minus n is divisible by 3 whenever n is a positive integer, just like that. So that's how you prove by divisibility. I don't know if I've got questions on this one. I don't know if I've got questions on divisibility, proof by divisibility, or on induction. So if there are no questions, I feel that I've talked too much. But I'm going to give you this slide. You are going to do.
Hello?
Yes.
Listen. Yeah,
Hello.
my name is Michael. My name is Michael from this province. I'm saying if I encounter a problem which I may have issues, is it possible for me to contact you?
Is it what?
Is it possible for me to contact you if I've got a problem which I fail to solve?
It's very, very possible. My DM is always open. I'm sure you have got my WhatsApp number, and we also have a group, right?
Yes.
Yeah. So Mikey,
Yes,
Mikey, what you are supposed to do, if you have got any challenge, before contacting me, post it in the group. Let's discuss it within the group. There's no need to put it in my DM. Yeah, that's the best thing to do. You can post it in our group, then we discuss together. Maybe sometimes I'll be offline, but there will be someone who will be online in our group who is actually ready to help you, or we have done that before. They can quickly share the solution.
Thank you so much.
Yeah, you're welcome. I don't know if I've got any other question. Otherwise, I'm going to share this slide. You need to look at trees. They're it's just very basic things. You need to look at a tree and then the graph theory part. So a tree T is a simple graph satisfying the following if V and W are vertices in T. There's a unique simple path from V to W. For example, here, the following graph is a tree since there is a unique simple path from any vertex in the graph to other vertex as well. So we can talk of rooted trees models. The rooted tree is a tree in which a particular vertex is designated as a root, like you have got this root and other subtrees. So this is an example of a rooted tree. And then there's this one, which is important terminology. Okay, so this one is about the terminology that we use in trees. The terminology that we use in trees, you need to be familiar with this. Let T be a tree with the root of V0 or V0 as the root here. So there's this terminology of total root, you and it. Suppose that X, Y, and Z are vertices in T, and that V0, V1 up to Vn is a simple path in T, then Vn minus 1 is the parent of Vn. If you look at that, we are saying that Vn will become the child of Vn minus. So it's like we are just going one step back. So that one will become the parent of Vn. So it's as good as if you are here at U, then this one will become the parent of U, something like that. And then V0, which is Vn, ancestors of what? Of Vn, the ancestors of Vn. It's as good as if you are looking at V here, this one are the ancestors of what? Of this V or of this W, something like that. And then Vn is the child of Vn minus 1. We are saying like this one, U is now the child of this. This one will become the parent, this one become the child. And then if X is ancestor of Y, then Y is also a descendant of X. It's as good as say this W become the descendant of the root. So it's like the family tree, something like that. So if X and Y are children of a Z, X and Y, if X and Y are children of Z, it means that X and Y are siblings. You can take of V and W here as siblings, V and W. I got my siblings. Why? Because they are both child of U. Something like that. So if X is no child, X is a terminal vertex or a leaf. You can talk of these ones. These are leaves. Those nodes or those vertices without children are called leaves or the terminal vertex. So if X is not a terminal vertex, so X is an internal node or internal vertex. So all those which are inside here, which are not leaves, they're internal, otherwise it would be a root. So also there is what we call a level. This is the first level, 0, level 1, level 2, level 3, up to level 4. So these three have got 4 levels. They've got 4 levels. It starts at level 0. It differs from height. Height starts at 1. So what else? Consider the rooted tree shown below with root V0. Sure, this one seen somewhere in your exams last time. So it's very simple. It's very simple. Just need to know that what is a level, what are descendants, what are children, what are siblings, what is the root, what is the height, you know, those basic things. If you are going to ask you to pick the leaves, which one are the leaves, something like that. So consider the rooted tree shown below with the root V0 or V0. So what is the level of V8? You need to look at it. The level of what? Of V8, this level 0, level 1, level 2, level 3, that's V8 there. What is the level of V0? 0. What is the height of this tree? 1, 2, 3, then 4, I think it's 5 as the height. So you just need to answer that. Here are the answers for you. The V0 is the root of V8, and then the level, this one is 0, the height is 5. Note that the level starts from 0 here. You need to know that the level starts from 0, 0, 1, 2, up to 5. Not up to 5, but up to 4. But for the height, you start at height number 1, number 2, up to 5. You need to know that. And then you are being asked of what are the siblings of V1. Look at V1. So the sibling is what? V2 here. Something like that. So that's what you are supposed to here, sibling of V1, V3, V4, V5. Where is V1? V1. The siblings of V1. It should be, what are the siblings of V1? You've got V1 here. The sibling of V1 is V2, not V3, V2, V5. The sibling of V3 will be V4 and V5 as the sibling of V3. Otherwise, V1, the sibling of V1 is this one. Why? Because they are sharing this same parent here. That's the logic there. That's the logic there. And then the children of V10, yes. So V3, V4, V5 are the children of V1. The children of V10 are V14, V15, and V16. So there's need of correction on the siblings of V1. There, it's not correct. The sibling of V1, it's not this, but it's V2 here. And then the descendants of V12, V17, V18, and what? Descendants of V12, where is V12? The descendants, yes, all those which are under V12, down there up to the end, they are descendants of V12. Yeah, so that's what you need to know. Then you can go on to binary trees. You can read of binary trees, those trees which say that a node can have maybe at least one child, but not more than 2, right? And we are taught a binary tree from the word binary tree. So it's either if you have this one, it is going to have 1, 2 children or just one child, right? Like here we've got this one, 2. Here we've got this one, 2. Here we've got this one, 2. But sometimes we can have this one which have only one child. So that's what we call a binary tree. So the children of any node in a binary tree are ordered into a left child and right child only. So a node can have a left and a right child, a left child only, or a right child only, or no child at all. So that's what you call a binary tree. There's a hand by Core. I don't know. You want to say something? If you want to say something, you can unmute yourself. Okay. Maybe it was an odd hand. So descendants is called the left subtree of X. So the full binary tree, it means that each and every node will always 2 children. Not more than that, not less than that. That's the full binary tree. That's the full binary tree. So that's the end of this slide. That's the end of this slide. I don't know if I've got questions on the trees before I talk about things that I want to talk about. So thank you for being here. It's now 2 hours something. I've been talking for a lot of time. Let me stop recording. I think